I'd like to introduce Professor Kourosh Kalanter-Zadeh. Kourosh is a professor of chemical engineering at the University of New South Wales. He is an ARC laureate fellow, and Kourosh's research interests are in analytical chemistry, materials science, gastroenterology, and medical sensors. Please give a warm welcome to Kourosh for his talk, Liquid State of Post-Transition Metals for 2D Materials, Interfacial Synthesis.
Thank you. Okay, thank you very much. So it's good to be here, Sushi and Manik, knowing that we have a research hub together, and hopefully this will be the start of this kind of presentations for the future. All right. So today I'm going to talk about liquid state of post-transition metals for 2D material interfacial synthesis. Liquid metals. If you look at the table of elements in this slide, the blue part, so the famous 6 elements that we always consider as post-transition metals: gallium, indium, tin, thallium, lead, bismuth. Thallium, lead, we always put them aside. The rest, gallium, indium, tin, and bismuth, are the ones that we can play with very easily. They're relatively safe. Indium, not as much, but bismuth, tin, and gallium are really safe in comparison to other materials like mercury and lead. Their melting point is very low. Gallium 30 degrees, tin 230, bismuth 270. We sometimes put the zinc group into this post-transition metals group definition, although something which makes them very comfortable not to, because the blue elements, the melting point is 330, but zinc is 420. Now, if you put that in, it becomes a bit distorted, the definition of low melting point liquid metals. Regardless, all these definitions and classifications are very difficult, and always there are some outliers. So we have fluidity, flexibility for these metals. When you melt them, they go to the liquid state. Now, the biggest difference is they are electronic liquids. Of course, we have gallium ions moving around, but we have lots of electrons that move around much faster. They're free to move around by several orders of magnitude faster than the ions. They can alloy and mix with each other at very high concentrations, and they have high thermal and electrical conductivity. Now, today I'm going to... Okay, so important properties of the metals which are used for synthesizing 2D materials are this list presented here. They hold liquid state at low temperature. Now, if you remember, when you grow, for instance, on wafer, graphene, you deposit something like copper, then you heat it up at around 1,000 something degrees. Because it melts, almost melts the copper. That temperature is very close to the melting point of copper. So actually, for the synthesis of gallium on a surface of a substrate, you use liquid metal. These are not new. But we're talking about, okay, how we can change the conditions to use post-transition metals with a low melting point for the same purpose. They mix with other metals so we can make catalytic reactive material with different interfaces. Very easily, you can do it in the kitchen environment, 330 degrees melting point. Everything you can do it in a very cheap, low-cost lab. You don't need any special equipment. They have atomically smooth surface like any other liquid. So templating two-dimensional material is the right thing to do with these materials. They have surface layering. I'll explain to you what they are, and have non-polarized core. Of course, when you grow something on the surface of liquid, you can just take tweezers and take them off the surface, the interface, and highly reactive. Okay. Now, the representative of this group is gallium, melting point 30 degrees. It's safe. It can alloy with zinc, bismuth, tin, indium at high concentration. and it makes very fascinating alloys. For instance, E-gain 75%, gallium 25%, indium, the melting point is 15.7 degrees. So it's a good rival for hazardous mercury because you can use it at room temperature as a liquid metal. Now, I mentioned about surface layering. So if you do X-ray reflectivity measurements for mercury, for gallium, for tin in melting in a liquid state, you see that you can see a peak, and this peak associates with the order on the surface. For mercury, you see that 2.2 angstrom. The surface layering is happening anytime you have an interface. It can be interface with vacuum, interface with vapor, interface with other liquids or solids. Okay, what does it mean? Surface become very, very ordered. Okay, let me go back and go forward. Good. So this ordering is very helpful. So when you expose gallium or other post-transition metals to ambient conditions, for instance, water vapor in the environment or oxygen in the environment, they oxidize. And this oxidation produces very highly ordered, sometimes not highly ordered, depends on the state of liquid that you're using, two-dimensional materials. So that's where we go towards two-dimensional materials. Gallium oxide is produced like graphene, like other two-dimensional materials. It's very strong across the basically two-dimensional material. It can make mechanical play mechanically with this kind of two-dimensional materials. For instance, you produce non-Newtonian rheological structures like this. Print gallium droplets on top of each other, and still it holds it, this two-dimensional material. Such a dense metal can be held together, and you go up, make three-dimensional structures. Now, let's go to the challenge of depositing two-dimensional materials on substrates. The first system for deposition of transition metal dichalcogenized, you can go and buy this equipment in the market now. Actually, every now and then somebody calls me, oh, we have a reactor, do you want it for the lab? They even forget that this reactor came from my own lab, right? We never patented them. So back in 2010, we actually developed this kind of reactors, not graphene, for transition metal dichalcogenized. Molybdenum disulfide was the first one that came from my lab. The problem is we always saw this, we can deposit two-dimensional materials using this kind of CVD techniques, right? The cheap ones are CVD that came from my lab. The problem is you always get these triangles. The size of triangles are large, sometimes go to 300, 400 micron, but still is not vapor scale. The center is always a seed which is very thick, and these triangles go on the top of each other, make double layer, or in the best case, they stitch together at the corners. So when you have electrons, they reflect, they scatter from those stitching points. It's not good. Other methods like MB, CVD, MB or ALD, you can use it, avoid the stitching, but they are cumbersome, high vacuum, other problems. MB is extremely expensive. So we use the nature, what the nature has given us, oxide or other materials two-dimensional on liquid metal. We just have to exfoliate them. It's on the surface of liquid produced. It's oxidized naturally based on Cabrera oxidation that happens. And if the surface of liquid metal is very large, you get single crystal as well. And you bring a substrate, stick it the substrate to the liquid metal, and everything sticks to this substrate, so you can harvest it very easily. Here, the example. This is tin, and as you see, this is more than two-dimensional because tin is not self-limiting. It becomes thicker and thicker in time, but you can take a piece of glass and remove the oxide from the surface. Imagine if it's a gallium, it's self-limiting, become two-dimensional. Of course, you cannot see in this video. right? Now, for oxide of tin, we reduce the oxygen, make it film also similarly. Self-limiting, if you bring the ambient oxygen from 21% of the room environment to only 1%, it becomes self-limiting. Then you bring a substrate here. We brought silicon substrate, and we just stick with hand, and we can harvest it. Tin oxide come out with touch of your hand. All one layer, very high quality, single crystalline. Sometimes you get single crystalline, sometimes multi-crystalline. Depends on the material that you're harvesting. Can be also pattern it and use it for making different devices. It's very simple. For instance, the example here, you put photoresist there, you put a mask, develop the photoresist, the areas that are not developed and removed. You can fluorinate those areas and put a droplet of liquid metal, for instance, gallium in this case, on the surface. Oxide sticks to the surface, and we use basically PDMS soft material to remove the liquid metal. You can wash the rest. What remains is gallium oxide. Gallium oxide itself is a wide band gap semiconductor. You can use it for making transistors, for power electronics, or you can reduce the band gap here. For instance, in a two-step, we expose it to sulfur, and we use gallium sulfide 2-layer, which has a much lower band gap, and make devices. But as you see, the photoluminescence of these stripes, even doing everything by hand, it's very homogeneously distributed. As you see, everywhere green and black. This was done by hand. Okay, now you can start with gallium oxide, tin oxide, and transform them into other useful material. One example, gallium phosphate, we expose it to hydrogen phosphate, and we produce gallium phosphate, two-dimensional material gallium phosphate. It didn't exist because gallium phosphate naturally is not two-dimensional. You cannot exfoliate it. But when gallium oxide is very thin, you transform it, you obtain the two-dimensional crystals. Of course, it's a very strange crystal. Then you have to persuade people what kind of crystal you're creating. Out-of-plane piezoelectric coefficient for this material was 7.5 picometer per volt. That was quite large. Actually, it's a very useful material as a piezoelectric that can tolerate very high temperatures. Or gallium nitride, famous material for making blue LEDs. Everywhere you are using it, in your mobile phones and also displays in front of you. So this time we use a precursor that has nitrogen urea, 800 degrees, transformed gallium nitride. Mobility is very high, and we use it for making some devices, which are not shown here. Another example. We talked about the ambient, which is oxygen. How about we change the ambient to something which has sulfur, like hydrogen sulfide? We did that, and what we obtain is tin sulfide this time. Tin sulfide is a P-type material. We did the measurement. Mobility was very high, 35 cm squared per volt second, one of the highest P-type two-dimensional materials ever reported in mobility of holes. A band gap of 1.4 electron volts. You can imagine you can use this for many electronic applications because we have access to lots of N-type material, two-dimensional material, but P-type obviously don't have access to high mobility. This one can allow you to make the right LEDs. But more than that, also piezoelectricity of this material was very high, 22 picometer per volt. Now, can we exfoliate tin sulfide? No. Although it's a layered material, it's a puckered two-dimensional material, exfoliation always causes the breakage somewhere. So directly making it like this allows the exfoliation of the two-dimensional material from the surface of liquid tin. And of course, we made this kind of devices that produce up to 200 volts and lots of current. As you see, it's a good piezoelectronic material. It was a record at the time. Or ITO. We can make ITO. ITO is used in your mobile phone, ITO, conductive conductive glasses. So it's made of indium and tin and oxygen. Indium and tin are both of them are post-transition metals. So we thought, okay, why not looking at a method of going from melt to making this kind of layers? Everybody is either sputter or a screen print them. I said, okay, this seems very simple. Why don't we do this? We did that. Melting it, instead of touch print, squeeze print, you can touch print. You make the one layer of this material on each side if you squeeze print, and the liquid metal goes away 200 degrees, and you can deposit it many times, just not one layer, two layers, three layers of that. You can make it much more conductive than the screen printed or sputtered ITO glasses, and more importantly, it's very transparent. Gives you 98% transparency after 2 or 3 layers of deposition. The mobile phone which are in front of you and still they're very good quality, for instance, Apple iPhone is 90-something%. This is 98%. So suddenly we are going one level up in the quality of displays. And it's two-dimensional. You can bend it. It's a new class crystal of ITO glasses. Or you can also use it for selective doping. For instance, here in this example, we put bismuth and tin together. Although in the core, you can mix and match everything you want. 10% this, 90% that, 50%. They go selectively to the surface. For instance, we put lots of bismuth in, only maximum 0.7, 0.6% of bismuth goes to the surface. So you are able to also selectively dope the surface and harvest them. Here the surface is dominated by tin oxide. Depends on how much bismuth you add to the core, then you can have bismuth doped tin oxide on the surface, right? And you can control the doping very selectively. And you can, as you see, put 1 layer, 2 layer, 3 layers on top of each other very easily. Now, surface of liquid metals are atomically smooth, right? And we have an interface which is very active. How can we use it for making other type of materials? So far we talked about layering of the surface. Now we're talking about the surface reaction. Interfacial effects, catalytic surfaces, and chemical reaction we can have to the surface. Here's one example, molybdenum disulfide. So one of the problems, as I mentioned, is the CVD that came from the lab was not very good. We wanted to find other ways of having single crystalline molybdenum disulfide at relatively low temperature, and gallium gave us that opportunity. So we put gallium, liquid metal, in acidic environment. Gallium is released as gallium ion and enriches the surface with lots of electrons. So we brought the precursor of molybdenum near the surface, and it produced hydrogen sulfide, very low amount. It's not really, we're not talking about even parts per billion, so it's not dangerous. And molybdenum disulfide produced on the surface. This time we didn't use hand. It was very difficult. We used a machine stage that goes up and down, nano size, piezo stage, and we could go down to 1, 2, 3 millimeters, large areas. We're not talking about micron anymore. And as I say, single crystalline, very good quality, any layer thickness that we wanted to. Even we could extend this to graphitic material. So we did DFT calculation. We saw that if we bring some precursors, organic precursors to the surface, and we apply a voltage in an electrochemical setup, then we can break them on the surface, dehydrogenate them. So methanol, ethanol, as a propanol, and the rest as you see. Acetonitrile, but pyridine. Some of them have nitrogen, some of them without nitrogen. DFT calculation shows that if you have doping, like adding indium and tin to gallium, this reaction happens better. Dehydrogenation happens faster. And also, more than that, the DFT calculation shows not only we can dehydrogenate, we can put CC bonds together. So we can make graphene oxide. And this is how it happens. If you don't have any of these precursors in the environment, surface remains shiny after 10-20 minutes. And if you have these precursors, surface becomes black and brown. Depends on how much voltage you apply. You can make graphene oxide. If you have nitrogen in your precursors, it becomes nitrogen doped, highly catalytic material, and the rest. And everything is done at room temperature. Interfacial effect of liquid metal is very interesting. For instance, if you put graphene oxide on a substrate, dip it into liquid metal, naturally it goes from graphene oxide to reduced graphene oxide very evenly on the surface. Here we showed the studies, and we wanted to make some devices. Dissonicated liquid metal together with graphene oxide on the surface becomes reduced graphene oxide, highly conductive. It becomes a very interesting material with interesting electrochemical properties. We did electrochemical characterization. We realized maybe we can use this for sensing. So we use it for dopamine sensing. If, for instance, this example is an example to show how we get selectivity of this. We have uric acid and ascorbic acid. If you do this sensing on the surface of graphene oxide, carbon surface, you can never tell the difference between the peaks of these groups. Now, because of using liquid metal at the core, we realized that we could push two of the peaks to each side, and as you see here, it became sort of very selective at a specific voltage to dopamine. And as you know, dopamine is a neurotransmitter. It makes us feel good. Many times we want to measure it as a neurotransmitter. So different concentrations, and these two peaks, they don't interfere with them. They separate themselves. You can go for high concentration, high material, high throughput production. This time, we can start from the core. How do we do this? We dissolve the secondary metal in the core, right? And then you apply the voltage on the surface. You disturb the equilibrium of the surface. You can bring the secondary material and put it into the core to the surface and spit them out. And that's very interesting. Still, we are studying it. For instance, if you have tin and other materials, many of the metals, they go into the core, come out as this milky thing after you apply voltage, right? But very interesting, if you put zinc or indium, then you see these black kind of plates coming out. So we characterize them. You realize the behavior is very different on the surface. So for instance, zinc comes at zinc core with zinc oxide coverage around it, this hexagonal shapes of zinc. And we can get really good quality large areas zinc oxide out or zinc out, depends on, for instance, how you change the pH of the environment. Very interestingly, tin comes a tin metal core and some tin oxide around it, but they come as round particles. So we can use the templating effect for some of the metals, not for others, depends on changing the condition. And the last one is, I just published a few days ago. I just wanted to say that even the smallest amount of impurity that you add to the core can change everything very significantly. Here we're talking about 0.0001% platinum. They added to the liquid metal, and suddenly the reactivity of this gallium metal from 1 went to 10 to the power of 3, 1,000 times, just by adding this metal. Just that much platinum to the core. You know, platinum is expensive, of course. If we can reduce the usage of platinum, it's a big achievement. If we can have the same reactivity of platinum, or even more than the same reactivity of solid platinum at room temperature, is an extraordinary achievement. Actually, what happened that when we did the DFT calculation, we realized that platinum is surrounded by several gallium, so they don't aggregate anymore. So platinum move around on the surface as liquid platinum at room temperature because of the gallium effect. So 1, and also activates the galliums around it. 2, this is why we have liquid platinum definition for the first time. So you can use your imagination. How you use liquid metal. increasing the entropy of liquid metals, but adding many different types of metals together, just solvents for metal, right? So you can imagine the movie Transformers, everything made of metal. The same thing. If you're in a different environment, then the DNA can be made of metals. So we can have a different mindset. Surface is layered. We can oxidize the surface, sulfurize the surface, harvest them. We can make things inside liquid metals, crystalline, think like crystallizing sugar and salt inside water. Here we're talking about crystallizing other metals into liquid metals and take them out. And it's a super catalytic material. Everything happens super fast. You can dehydrogenate organic material, make CC bonds, and you can use your imagination. So I would like to thank you for being here and listening to the talk, and happy to take your questions.
Really exciting talk. So I guess a couple of questions. So when we are using the liquid metal approach for synthesis, the most important aspect is the interfacial aspect, the interfacial area. And so when you're making these 2D materials like gallium oxide, you have a thin layer of oxide forming, which you can transform into different species. So would we have generality in making material like, for example, molybdenum disulfide or the different types of TMDs? Can you use that approach to make more generic 2D material? You have shown, and in fact, you do that to make a 2D molybdenum disulfide. So how generic is the process?
Yeah, that's a very important question. First of all, we have oxide. Oxide is not always our friend, sometimes our enemy, because it basically buffers the very active catalytic surface of liquid metal. We don't want that. So, for instance, if you remember, I mentioned that we used acid, right? And here, we use acid to produce gallium 3+. So they go, and then we have a precursor of molybdenum disulfide that produces the molybdenum disulfide on the surface. Or here, it was done in a basic environment. We have NaOH to get rid of that oxide again. Now, very interestingly, we still don't understand this oxide. We realize it's not our work, it's published by another group. But we also tried it. We realized even when we do CVD on gallium, without even considering that oxide is not there or it's there, and it's a mystery for all of us. Now, it has been for 1 year the paper was published. We repeated that it works. It's not a fake paper. At 200 degrees CVD, you can deposit graphene on gallium. So is it the oxide which is helping, or it's the gallium which is something is reacted on the surface that removes the oxide at the same time of deposition? We try to find out exactly what's happening there, and still there's a mystery. Okay, now, saying those things. So we're talking about deposition in liquid media and gaseous media, and then how we can expand it to other metals, other metal compounds or other materials. For instance, we try to do it to tungsten. We couldn't, because all the numbers were very different from molybdenum, right? So we couldn't find the precursor in liquid to do this for tungsten sulfide or tungsten selenide. But I'm sure, somebody can formulate that. We couldn't. I'm from telecommunications background. I don't have that kind of knowledge. But interestingly, it's the same as graphene. CVD graphene, people eventually realized, okay, iron or copper are the best catalysts to start with on a substrate. Eventually, it should be narrowed down for a specific material that you want to deposit to a specific formulation. And I'm sure for any formulation can be found, because exactly, you have so many options of so many mixtures.
Question online, I'll read it out.
Yeah.
So the question is from Yun Ho Kang. They say, thank you very much for your nice talk. I have been interested in your many works on liquid metal-based 2D material. I have two questions. One, the contact angle of liquid metal seems somewhat high on its original substrate. Does lowering the contact angle help film transfer? Two, is it also possible to make heterostructures with other 2D materials? Example, aluminium oxide, zinc oxide, etc.
All right. So very interesting questions. Thanks. Contact angle is very different from ionic liquids or other type of liquids. Actually, we were thinking it's very simple. We go and measure the contact angle. Eventually, we realize we can have any contact angle on the surface. Depends on how much material we add to the surface. So, yeah, and how much oxide we have and the rest. So it became everything that we knew for 10 years publication. It seems that all of them are wrong, because there was a paper published that showed you can do any contact angle with anything you want, depends on the environment. Okay, so it's an open question, the contact angle measurements for liquid metal at the moment, rather than closing it. And the other one, yes, we can deposit different layers of different types. At the moment, for instance, we're looking at ITO and ZHO, which is ferroelectric material. We are just working on it right now in our lab. So having heterostructures using this process is very possible, and I think it's the next steps to do.
Yes, because we are an energy group, just wanted to also touch upon that there has been pretty big progresses in using liquid metals for batteries. I know MIT have a pretty big startup. They're looking at a lot of money. So what is the advantage of using liquid metal in batteries? I think I'm intrigued by that question.
So it comes in two different parts. One is using them for electrodes. Yeah. The other one is to use them for the electrolyte. Okay. Yeah, it's possible. So you increase the temperature to above 200 degrees, and it's very cheap. Actually, if you go above 250, you can use tin, and it's the cheapest thing. It's cheaper than water. But electrolyte, I mean, you have to do that. So then everything goes into liquid electronics. So I can send you some of the papers as to how to deal with it. So sealing, dealing with it, how to make sure everything operates at 250 is going to be very challenging, but it's possible. But because of these difficulties, most of the focus are on the electrodes. And they're good materials. Conductivity is high. You can increase the surface area very easily by just sonicating it. They mix really well with graphene and other materials. Anyway, it was a part of very old batteries. So we had mercury batteries, gallium batteries forever. Mercury was a part of, always an essential part of any battery till 80s. So,
all right, that's good. I guess any other questions?
Yeah.
Yeah, my question was about, you showed that you can make some piezoelectric materials as well. So some of the constants that you show for piezoelectricity is much lower than some known piezoelectrics like PZT, 120 picometer per volt, and even higher. Nowadays with intercalation 2D piezoelectric materials, for example, which go to a few hundred picometers per volt. So do you see any method or anything that it can be improved, or because some of them are through basic calculations rather than measurements. So is there a limit theoretically on what it can be achieved, or it's just a formulation?
Okay, so PZT and others, you cannot bend them at the moment, the PZTs we have. You bend them after some degree angle because it's either sputtering or basically printing methods. They break. So these ones that I'm showing to you is about the very different technologies, the piezotronics, right? So you bend them and you want 2D material to bend. Is it possible to increase it? is about how you decrease the symmetry as much as possible. So Parker, the structure of tin sulfide was one of the best. Now we're talking about only pure materials. As impurity, you can go up and up and up. DFT calculation shows that you can go to 400 picometer per volt. That gives you around 3 volts when you bend, for instance, your finger if you make a device from it. And it also produces lots of current because this material is a semiconductor, right? So we showed the record of 0.15 or 0.2 volts. Increase it to 2 volts and you have a current. This is real, okay? And this is two-dimensional. This is really two-dimensional. We're talking about 0.7 nanometer thickness. So it's a very different field.
So I guess you have the added advantage of being flexible, right?
Yeah, and it doesn't break.
Yeah.
You can bend it.
Yeah, sorry.
Yeah, you can bend it millions of times and it keeps its integrity.
All right, no, I guess that's all I have to say. Thanks.
Thank you, Kourosh. Please thank Kourosh again. Thank you very much.